In this video, we're going to look at modeling with differential equations. We're not going to go real in depth into it. That's going to be later in the quarter and later videos. So right now we're just going to explore some very basic modeling with differential equations. And to do that, I want to first start with introducing what a slope field is. So here's two examples of a slope field, and basically what it is, it's a collection of arrows that are drawn tangent to the solution curves. And this will give us information about the differential equation and the solution that we are hoping to find. We're going to go more in depth in this into chapter 2, but I did want to introduce these now. So it's in the book, so I just thought I'd throw that out there to have you start to think about what a slope field is. So one of the things that we will see differential equations in is physics. Now we know that the derivative of the velocity is the acceleration, and that's going to be equal to the mass multiplied by the acceleration gives us the sum of the forces. In free fall then, the mass times the acceleration due to gravity is mg, minus this k, which is the coefficient of friction due to the resistance to the object with respect to air, and the velocity v of t raised to some power p, assuming that power happens to be 1. We have this is the differential equation. Now, if we solve the differential equation, we're going to get the velocity v of t is equal to the mass multiplied by the acceleration due to gravity, g, divided by k, remember k is the coefficient of friction, plus some c, e raised to the negative kt over m. When p is not equal to 1, this is a nonlinear differential equation and much harder to solve, so we're not going to worry about that right now. As t goes to infinity, the velocity is going to go to the terminal velocity. In other words, it is the maximum velocity that's going to happen when the object falls through fluid, in particular air, is what we are going to be looking at. So here's an example. We have an object with a mass of 10 kilograms it's projected upward with an initial velocity of 40 meters per second. Assume the forces acting on the body are gravity and air resistance, with a direction opposite to the direction of motion, and the magnitude of k being our coefficient of friction, multiplied by the absolute value of the velocity, where v of t is the velocity at the object at time t. Find a differential equation for the velocity in terms of k. So what we're going to do, let me just move this up so I can have some space, is that we know that m of mass multiplied by the derivative of our velocity is going to be equal to mg, minus k v of t raised to the first power. Now we're going to solve for v prime of t, which we know. And we're going to get v prime of t is going to be equal to gravity, because I'm going to divide both sides by m, minus, and this will be k, v, I'm just going to write v instead of v of t, divided by m. Now, m happens to be 10, so v prime of t is going to be gravity, which is 9.8 meters per second, minus kv divided by 10. And it's 9 meters per second because of the fact that we are in metric. Now we want to solve the differential equation from part A, which was what we just found, for the velocity at any given time. Now we know that v of t is going to be equal to mg divided by k plus ce raised to the negative kt divided by m. We know what m is. M is 10, so this becomes v of t is going to, and we also know what g is, so it's 10 multiplied by 9.8 divided by k plus ce raised to the negative kt divided by 10. We're also given an initial value. So v naught, which we were told is equal to 40 meters per second. So we know v of 0 is going to be equal to 10 multiplied by 9.8 divided by k plus ce raised to the 0, and this has to equal 40. So we know that c, because e is equal to 1, c must be equal to 40 plus 98, that's 9.8 times 10, divided by k. Now I need to stop and make a correction here. Gravity is going in the opposite direction of our velocity, so this should be a negative 9.8. And this is a negative 9.8. So that's why when I bring it to the other side of the equal sign, the 98 over k, that's why it becomes a positive 98 over k. Don't forget the directionality. So my v of t then, v of t, is going to be equal to the negative 98 over k. K is just a parameter, plus 40 plus 98 over k multiplied by e raised to the negative kt divided by 10. So this is my velocity at any given time. And all I need to know is what the friction to the air, remember what k was the coefficient of friction due to the air resistance of the object. So I need to know that parameter, and then I could tell you at any given time what the velocity of this object is. Now I'd like to find the limit of this velocity for some fixed time t naught as the air resistance of coefficient goes to 0. So I'm going to do the limit as the resistance goes to 0 of this equation, which was negative 9.8 over k plus 40 plus 9.8 over k e raised to the negative kt divided by 10. Now, just to make our lives a little bit easier, I'm going to make this one single fraction, because right now I have e raised to the negative kt. E raised to the negative kt really should be in the denominator, so this really is a fraction. And so I want to go ahead and clean this up so that it's the same fraction. And when I do that, I'm going to end up with a limit as k approaches 0 of negative 98t divided by 10 e raised to the kt divided by 10 plus 40, all divided by e raised to the kt divided by 10 plus ke raised to the kt divided by 10 multiplied by t divided by 10. Now, I can let k go to 0, and the reason I couldn't do that before is this would make it undefined, and of course I used a little bit of L'Hopital's in here, so I did some algebraic cleanup, and then I did L'Hopital's L-hop. So I did some algebra in here, and I did some L'Hopital's, and now I can do a direct substitution when k goes to 0, and I get negative 9.8 t plus 40. And so there it is, the limit of the velocity for some fixed time t as the air resistance of coefficient goes to 0. And we see this a lot. Now, when we go back into pre-calculus 1 and we're looking at a projectile, we see this a lot. We actually see this in calculus 1 as well when we're trying to find the velocity or the acceleration at some given time. You're going to see this initial velocity and gravity going against it. So that when you see that and you don't see anything else, the assumption is that the air resistance is not important for that particular problem, or we just decided to ignore it completely. Another place that we're going to see differential equations is in mathematics. So if I wanted to find a parameter family of curves that satisfies y is equal to the f of xc, and I want them to be orthogonal to the family of y bar is equal to the lowercase f of xc. Well, remember, the uppercase is the antiderivative of the lowercase f at each point xy plane. Then the two family of curves must have slopes that are negative reciprocals for each other at every point on the xy. So here is I just need to erase this. It just keeps coming along for the right, and I didn't want that there. So find the orthogonal trajectories for the family of curves where y is equal to c to the x. So the first thing I'm going to do is I'm going to do y prime is equal to ce to the x. And so the differential equation is y prime is equal to y. So then we replace y prime with negative 1 over y prime because we want the slopes to have negative reciprocals. So actually I shouldn't say y prime equals, I'd say y prime gets replaced with negative 1 over y prime. And so I have 1 over y prime is equal to y. This then becomes y prime is equal to 1 over y. And so I have a differential equation that has the orthogonal to my original one. So I want to find the general solution for this. When I dropped my negative, man, look at that. It should be negative because I want to have them negative reciprocals. And so this becomes a negative here. I'm going to go ahead and multiply both sides by the negative y. So I'm going to get y, negative y prime is equal to 1. So that tells me that negative y prime minus 1 is equal to 0. So in other words, y prime plus 1 is equal to 0. And this is a separable differential equation. If this is a separable differential equation, then I can replace y prime with dy dx. So y dy dx plus 1 is equal to 0. That means I can then say, wait a minute, y dy is equal plus dx, not equal, plus dx is equal to 0. We like that. Now I can integrate this. So I'm going to integrate my y dy plus the integration of dx plus the integration of 0, which is 0. And this will equal 0. And I'm going to integrate the 0. But remember, when I integrate the 0, it's not going to be 0. It's going to be, I'm going to do it with respect to x or y, doesn't matter. It's going to give me a constant. That's what I know. So when I integrate this, I'm going to get 1/2 y squared plus x is equal to some constant. That tells me that if I multiply everything by 2, I'm going to have y squared plus 2x plus 2c, equals 2c. But guess what? 2c is still just a constant. So I have y squared plus 2x plus or is equal to c. I don't know why I keep wanting to say plus. It is equal to c. That tells me the family of orthogonal trajectories to this original function is these. And if I were to draw these, my original family of function of y equals e to the c are going to look something like this. If I were to draw my y squared plus 2x is equal to c, it would look something like this. And so you can see with my really poor drawing that those family of functions are going to be orthogonal to the other family of functions. So that's kind of cool. Here's another example that you might see in math. A curve passes through the point 0, 3 and has a property that the slope of the curve at every point P is 5 times the y coordinate of P. What is the equation of the curve? So what that's telling us is that y prime must be equal to 5y. And this only happens when y is equal to e raised to the cx. We know that's the only time it happens. To have a y-intercept of 0, 3, the only way that's going to happen is if the coefficient on this happens to be 3. So y is equal to 3e to the cx. And the only way I can get my output to be 5 times as large is if my C value happens to be 5. So my answer is y of x is equal to 3e raised to the 5x. And that was just using the information that's given to me, some general information about differential equations, some general information about derivatives and exponential functions in general. So that one's kind of cool. Let's take a look at this example when we're looking at engineering. So the current, labeled I of t, in amperes, is a simple electric circuit. It contains a resistor, an inductor, and a sinusoidal electromotive source, and can be modeled by this equation. L of I prime of t plus R I of t is equal to P sine of t. Well, L is the inductance in henries, R is resistance in ohms, and E of t is equal to P sine t is a periodic electromotive force in volts, sometimes noted just by V. Kirchhoff's voltage law is what it is. And solving for the I prime of t, we get this. And that's because the equation of this linear solution and constant coefficients, our general solution is this, which is sometimes wrote as this. And I'm not going to lie, I have an engineering background, but mine's civil engineering, and I tried to avoid circuit theory like the plague because I was more interested in structures. So I'm sure there are a lot of you who's like, well, you're not saying all these words right, and you're probably right, and I'm okay with you saying that to me because I am a civil engineer by trade and not electrical engineer, and I try to avoid all the circuit theory classes. And in fact, you'll talk to any engineer that has gone through and got their degree, and they're going to say, oh yeah, there was one class that just gave me a hiccup, and mine was circuit theory. I ran at it twice, and I dropped it twice, and that's when I decided, I freaking like structure, so let's focus in on structures. So that's all I'm going to say about that. Let's look at the example, though, because there's some places in which this has a lot of sense. So suppose we have a circuit whose battery supplies a voltage of 30 volts, and the resistor is 300 or 30 ohms, and the inductance is 2H, and I of 0 is equal to 0. Find the current in amperes of t seconds after the switch is closed. By going straight to the very last equation, and this is something I really love, is I'm going to get I of t is going to be equal to 30 over 30, because my voltage and my resistance is the same thing, numerically. 1 minus e raised to the negative 30t divided by 2, which is basically going to give me 1 minus e raised to the negative 15t. Done. Done. Another place that you will see differential equations is in ecology. And we talk about logistic growth models in pre-calculus 1. In fact, for good or bad, I used to talk about logistic growth models in viruses, which of course, being this 2022, the tail end, hopefully, of the pandemic, I don't want to go any further into that. However, here's what we end up with is P of t is equal to n over 1 minus CE raised to the RT. This is really, really nice. We can use this for when we can only have an ecosystem that can only take so much, or when we did viruses, the virus can only infect so many people. Let's use this. And it says, suppose a lake is stocked with 600 fish, and we want to estimate the carrying capacity, or the estimated carrying capacity is 5,400 fish. The number of fish double in the first year, assuming the size of the fish population satisfies the logistic equation dP dt is equal to Rp, 1 minus P over N. Determine the growth rate. Okay, so dP dt is going to equal to R 1 minus P over 5,400, 5400, because that's our that is our carrying capacity, that's our N, and then multiplied by P. Now we also know that P of 0, our initial population, is 600 fish. We also have that P of T has to be equal to, and this is coming from right up here, the 5,400 over 1 minus CE raised to the negative RT. Now, we know that P of 0 has to be equal to 5,400, 1 minus CE raised to the 0, which has to equal 600. This gives us, when we solve for this, we get C is equal to negative 9. So now where I am is P of T is equal to 5,400, 1 plus 9, E raised to the negative RT. Now, we also have the second initial condition, which is after 1 year, when T is equal to 1, our fish have doubled. So P of 1 is equal to 5,400, 1 plus 9E raised to the negative R multiplied by 1, and this is equal to 1,200 fish. Now solving for this, I'm going to get a rate of 0.944616. So the equation then is P of T is equal to 5,400, 1 plus 9E raised to the negative 0.9446, I'm just going to go to that many decimal places, times T. Now I want to know how long is it going to take for the population of the fish to be 2,700. So P of T is equal to 5,400, 1 plus 9E raised to the negative 0.9446T is equal to 2,700 fish. Doing my usual pre-calculus 1 solving, and I'm going to get T is approximately equal to 2.32 years. And that's it for this video.